So here's a nice simple example. I'm going to sketch the region above the xy plane, and under the paraboloid f of xy equals 4 minus x squared minus y squared. That's like a three-dimensional version of a parabola. Here you can see it from the side. It looks like a parabola if you just look at it strictly from the side, but keeping in mind it's the surface is it's a hollow object, if you want to call it that way, if you look at the surface, but it could be a solid object. And this plane cuts off the nose of it. Looks like the tip of a bullet. And I defined this function h so I could draw the xy plane. That's what that hot pink colored plane is. So hopefully you can see the solid region under the graph of f and above the xy plane. In other words, what's inside this cage, more or less. So we can find this volume in a rather simple way using a double integral. We obtain the integral by allowing the largest of the delta xi and the delta yj in a Riemannian sum to approach 0. Hence, the area of the rectangle, delta A of that particular rectangle, approaches 0. And before we do that, let's try to approximate the volume under this graph, but above the square, between x going from -1 to 1, y going from -1 to 1. I know that's not the particular one we're examining right here, but let's just see how to do this with a square and how to do what's called the upper sum and the lower sum. So if we use the Riemannian sum with delta x and delta y fixed at length 1, of course that's not approaching 0, but fixed at length 1, then that's actually, that is 4 squares. This region would be giving us 4 squares. The volume is somewhere between the upper sum, as if we pick the largest possible value for f of x, and the lower sum, as if we pick the smallest possible value for f of x over that square. Okay, the upper sum uses the largest possible value for the height of f, and the lower sum uses the smallest possible value. So, of course, the area of each of those rectangles is 1, because, like I say, with delta x and delta y fixed at length 1. So one of them would be x going from negative 1 to 0, and also x going from 0 to 1, but y could also go from -1 to 0 and 0 to 1, so that would be 4 squares. So the upper sum would be 4 rectangles, and then this is from the function 4 minus x squared minus y squared. And since we're subtracting the x squared and the y squared from 4, this is going to be a maximum if the x and the y are both 0, and our upper sum would be 16. Now the lower sum, we want to pick the smallest possible values for f of x, and on that particular square of this particular function, the smallest values would of the function occur when x and y are both 1, or technically both when they're both -1, but still this would be the same at 2, 4 minus 1 minus 1. So 4 times 2 is 8. So the lower sum is 8. So our actual integral of this is somewhere between the two. Now keep in mind, that is not this region here between the plane and our function. That's the region over a square, and you'll see a picture of it here in a little bit. So with a finer mesh, we could get a better approximation. All we know about this one is somewhere between 8 and 16. That's not real accurate. So if we had a finer mesh, we could do that. I think it's too much bother to do that, but even using an interior point for evaluating the function would improve our approximation. In other words, I just used, for every one of them, I used the point at the top and then the point as close to the bottom as I could for the lower sum. An interior point might improve the approximation, but this was just to be instructive. The exact answer we can obtain from a double integral, and this is it. The definition of a double integral over the region R of a function f of x, y, and this dA represents, I don't know what order I want to integrate in, so dA is dy dx or dx dy. For now, we'll learn some other ways of representing that, but not at this time. But that double integral is the limit as delta A approaches 0. Now what that means is that the length and width of our rectangle is approaching 0. Of this double sum, the double sum we brought up way back here. So, provided that limit exists, of course, and if the limit exists, then f is called integrable over the region R. If that limit doesn't exist, well, then it's not integrable. Probably something gets outlandishly undefined. So, the size of the small rectangles approaching 0, or delta x and y, delta xi and delta yj are both getting infinitely small. So the volume of this solid region, that is over some region R in the xy plane and under the graph of f of xy greater than or equal to 0, right? We assume that that's true, is given by this double integral. So calculate with a double integral the exact area under the graph of, and here we're finally doing it, our function up here, and above the square where absolute value of x is less than or equal to 1, absolute value of y is less than or equal to 1. Do you realize that that is the same as what I was describing in this region right here? Okay, so hopefully you realize that. So we can do that just by saying it's the integral, and it wouldn't matter which one you did first, dy or dx. So we're integrate this one with respect to y first. It'd be 4y minus x squared y minus y cubed over 3. Y going from -1 to 1. Put those numbers in there. You should work this out. Instead of me doing it, you should work it out, because we learned how to do double integrals in the last lesson, so you should be okay with that. And then after you integrate that, take that result and integrate it with respect to x, also x going from -1 to 1. And hopefully you would get 40/3. If you want some details on that, I guess I could copy this and show you a little more detail than that. My first integral is going to come out 4y minus x squared y minus y cubed over 3. So 4y, let me see, 4y minus x squared y minus y cubed over 3. And if you look over here at this thing, you should see how that works out. Oh, my 4 is not supposed to be out of the parentheses like that. Let me see if, there we go, that's much better. And that is to be evaluated, whoops, to be evaluated from y going from -1 to 1. So let's see what we get there. That will give us 4 minus x squared minus 1/3 minus, maybe I need to write this in greater detail. That would be integral from -1 up to 1, and that's 4 minus x squared minus 1/3 and that needs a parentheses around it. And then, oh, what happened to my parentheses there? I put one there and it didn't take. Okay, then I'll say minus. Maybe I can get the parentheses in there now. Lefty? No. How about a righty? A lefty? Now it'll go in there. That's better. And then, if I put in -1, then I guess I'm just going to get 4 again. Minus, if y is -1, no, I'm sorry, that's going to be minus -4 then, isn't it? Minus -4, because if I put -1 in for y, that's going to be -4, and then minus, -1 goes in there for y, so that's going to be plus x squared, and then putting -1 in for y, this part's going to be minus -1 cubed over 3, so minus negative 1/3, so I'll say plus 1/3. And this mess, well, that's dx. This mess needs to be simplified, so let's see if we can work that out. That would be 8 minus 2x squared minus 1/3. So, well, or minus 2/3. So 8 minus 2/3 would be 7, and 1/3, that would be 22/3 minus 2x squared. So that's it, 22/3 minus 2x squared. And we're now integrating that with respect to x. And so I guess from that, we should see 22/3 x minus 2x cubed over 3, and that to be evaluated between -1 and 1. So, oh, sorry, -1 and 1. I meant to type a 1 there. So, all right, now hopefully you can see when I put a 1 in there, I get 22/3 minus 2/3, which is 20/3. When I put a -1 in there, that would be minus a negative 20/3 again, so I do wind up with 40/3. That's what I wanted to show you, and I know I should have said you can work that out yourself. I let my software do it, but I did it myself. Thank you very much. Okay, but you should have been able to do that without too much hassle. And what we got, the answer, here's a picture of what we got. I can't rotate this one because I had to copy it to make the picture nice. But the XY plane is this black thing down here, and underneath this paraboloid and over the square, x going from -1 to 1, y going from -1 to 1, we got the volume of this thing that looks a little bit like a loaf of bread. So that's my best attempt at that sketch, and there it is, all done. And hopefully you understood all that.